Now we will start. In today's lecture, we will see theory of forced oscillations. In earlier lecture, we have seen damped oscillations. So here, this one is differential equation for damped oscillations. This second term represents damping force. This third term represents restoring force. And we convert this into this differential equation where 2 gamma is equal to R upon M and omega 0 square is equal to K by M. Here K is force constant, M is mass of the oscillator. If we solve this differential equation, we get solution. X is equal to this. In last lecture, we have seen this. And we have also seen three cases. Damping force greater than restoring force, that is called overdamped motion. Damping force equal to restoring force, that is called critically damped motion. And damping force less than restoring force, that is gamma is less than omega 0, because this gamma, it is measure of damping force. This is measure of restoring force. So when gamma is less than omega 0, we get solution like this. X is equal to A e raised to minus gamma t sine pt plus theta. Here this P, it is angular frequency of damped oscillations. And this P, we have this P is equal to square root of omega 0 square minus gamma square. So here P is less than omega 0. So decrease in angular frequency and increase in period, that is characteristics of damped oscillations. So we have also seen one example. We have taken spring mass system. It is placed in resistive medium, maybe air, and if we displace this spring mass system is here like this, we have extended this one, and if we release this, it oscillates for this condition, damped oscillatory condition. But if we see, amplitude goes on decreasing and finally it will come at rest. So if we see again, we have displaced here. So this is equilibrium position. We have displaced and then released. So it is oscillating, but its amplitude of oscillation goes on decreasing and finally it will come at rest. So if we plot graph of x versus t, if we plot graph of x versus t, you will get graph like this. So here amplitude of oscillations that decreases exponentially. Amplitude of oscillations decreases exponentially, and this amplitude is A e raised to minus gamma t. We have seen multiple choice questions on this also. Now we will go to forced oscillations. So what is meaning of forced oscillations? So when we set system into oscillations in external medium, and suppose damping force, it is less than restoring force, the body will oscillate, but its amplitude of oscillation will go on decreasing. So energy of the oscillator also decreases with time. That energy, it is used against the external resistive force, and finally that oscillator comes at rest. Suppose we want body to oscillate continuously, then external periodic force is applied on the body. When we want body to oscillate continuously with some amplitude, we have to apply external periodic force. And when body oscillates due to that force, that oscillations are called forced oscillations. So if we see in forced oscillations, we have three forces now. So first force, that is F1 is equal to minus Kx. This is restoring force. Now second force, that is damping force. F1 that is proportional, F2 that is proportional to velocity. So we take minus R into dx by dt. Dx by dt is velocity. This is called damping force, which opposes the motion. This restoring force, it tries to maintain motion, but due to damping, amplitude goes on decreasing. We want body to oscillate with some constant amplitude, so we have to apply external periodic force. So F3, we can take F0 sine Qt. This is periodic force. It is also called driving force. It is also called driving force. And what is Q? Q is angular frequency of applied force. And F0, that is amplitude. Amplitude of force. Force means applied force. That is maximum value of force, because sin Qt it varies between +1 and -1. So F3 it varies between F0 and minus F0 through 0. So what happens? Total force F is equal to minus Kx minus R dx by dt plus some F0 sin Qt. And we know we can write this force as mass into acceleration. So m d2x by dt square is equal to minus Kx minus R dx by dt plus F0 sin Qt. This is external periodic force applied on the body. So what happens here? So we get here differential equation. This is differential equation. M d2x by dt square plus R dx by dt plus Kx is equal to F0 sin Qt. So this is second order linear and non-homogeneous. Non-homogeneous differential equation. So this differential equation, now here we can convert this into this one by dividing throughout by m. We get R upon m, K by m, F0 upon m. So what is 2 gamma? 2 gamma it is R upon m. Omega 0 square it is K by m. And small f0 it is capital F0 upon m. So here we get this equation. Now this is second order linear and non-homogeneous differential equation. Now this differential equation has two solutions. One is called complementary function and second one is called particular integral. Now what is complementary function? Now this complementary function, it is solution of homogeneous part. Solution of homogeneous part means homogeneous part is what? d2x by dt square plus 2 gamma into dx by dt plus omega 0 square x is equal to 0. And we have already seen its solution for damped oscillations. X is equal to a e raised to minus gamma t sine pt plus theta. So this is solution for homogeneous part, means this one. This is called complementary function. And particular integral is what? Particular integral is the solution of this differential, whole differential equation. So we will assume that solution as x is equal to a sine qt minus phi. A sine qt minus phi. We will assume this. So if we assume this solution as particular integral, we get solution like this. X is equal to a e raised to minus gamma t sine pt plus theta plus a sine qt minus phi. Now see here, this first part, it is called complementary function, and this second part, it is called particular integral, where we have two constants a and phi. These are two constants that we have to determine. Now see here, for first part angular frequency is p, and for second part angular frequency is q. So what is actual frequency of the oscillator? So what happens when we set oscillator into oscillations by applying external periodic force of angular frequency q? Now body has natural frequency, angular frequency p. Initially body will neither oscillates with p or with q. It will oscillate in complicated manner, whose frequency is neither equal to q or nor equal to p. But as time passes, if we see this solution, this is transient solution. This is transient solution. Transient means it decreases with time. And after sufficiently long time, this first part will become zero. And remaining solution will be what? Remaining solution will be second part only. So what is remaining solution? So we'll get this one. X is equal to a sine qt minus phi. And body will oscillate with frequency equal to frequency of applied force. So in forced oscillations, for initial some time, frequency neither equal to angular frequency nor equal to neither equal to its natural frequency nor equal to applied frequency. But after some time, body will oscillate with frequency equal to frequency of applied force. So we have this solution. Now if we use this here, now we have to find a and phi. If we use x is equal to a sine qt minus phi and adjusting terms, we will get a. Means here, if we use here or here, we will get a. That is also amplitude of oscillations. A is equal to f0 upon square root of, in bracket, k minus mq square bracket square plus q square r square. Or you can write this as f0, here small f0. We know small f0, it is f0 upon m. And gamma is equal to, means 2 gamma is equal to r upon m. So it is r upon 2m. And omega 0 square is equal to k by m. So you can convert this into this. f0 upon square root of omega 0 square minus q square bracket square plus 4q square gamma square. So what happens here? If we see amplitude, it depends on this term. Omega 0 square minus q square. Omega 0, it is natural frequency of the oscillator. Means when oscillator we set into oscillations, it will oscillate with that frequency when there is no external periodic force or resistive medium. So this is called natural frequency. Natural frequency. So amplitude, it depends on this factor. And phi, that another constant. So we can find tan phi. is equal to QR upon K minus MQ square, or 2Q gamma upon omega 0 square minus Q square, tan phi. What is phi? Phi is shear. This is displacement of the oscillator. This is applied force. So if we check phase of applied force, here it is QT, and phase of displacement, it is QT minus phi. So it is phase difference between applied force and displacement. That is tan, and that is given by tan phi. So phi is tan inverse of this. Phi is equal to tan inverse of 2q gamma upon omega 0 square minus q square. This is phi, phase difference between displacement and applied force. Now we will see simple example here of damped oscillations. Now we have here spring mass system, and suppose this is medium, okay, medium, and suppose this mass is magnet. This mass, it is magnet. So this suppose lower pole is south pole, upper pole is north pole of this mass, and here we have placed here. This is equilibrium position. Now we know when we extend this and release, it will oscillate, and if damping force is less than restoring force, it will oscillate, but its amplitude will go on decreasing. We want it to oscillate with constant amplitude. We have to apply external periodic force. So here I have taken mass as a magnet. That mass is magnet, some magnet. Lower pole is suppose S pole, upper pole is N pole. And suppose we take here coil. And we know if we pass current through the coil, what happens? Magnetic field that is induced in the coil. That is induced in the coil, like this. And it will either attract or repel the coil, repel the mass, because mass is magnet, and that depends on what direct means the pole of this. If it is S pole, lower pole is S pole, so what happens? It will repel. If this pole is N pole, it will attract. It will attract. So here direction of magnetic field, it is decided by direction of current through the coil. Direction of current through the coil. So suppose if we apply alternate current, so I will take here AC source, we will adjust frequency of that AC source, and we will apply between these two. So what happens? This mass starts oscillating. This mass starts oscillating. Now what happens here? Since it is AC signal, alternately direction of current will change. So alternately direction of magnetic field will change. Also intensity of magnetic field will also increase, decrease, because this is AC signal. AC signal. And now what happens here? This mass will oscillate, means this spring mass system will oscillate with constant amplitude. And that amplitude, it is decided by this difference. So omega 0, it is natural angular frequency of this spring mass system, and Q, this is frequency of applied EMF. Frequency of applied EMF. So here amplitude is decided by this one. And now you can change. You can change frequency of applied EMF. According to that, amplitude will change. So what happens in this case? Whatever amplitude of oscillations, here this is equilibrium position. From equilibrium position, it goes up to this, and it goes up to this. So this is amplitude A. Amplitude A is decided by what? This difference. This difference. So when now natural frequency is constant for that oscillator. So when we change frequency of applied force, here frequency of applied EMF, this amplitude will change. It will either increase or decrease depending upon difference of this bracket. Depending upon this difference. So we'll see this. Now, so we have this amplitude. A is equal to F0 upon square root of omega in bracket omega 0 square minus q square bracket square plus 4q square gamma square. And tan phi is equal to QR upon K minus MQ square is equal to 2Q gamma upon omega 0 square minus Q square. Now what happens here? So amplitude C depends on this denominator. Amplitude is small when denominator is large, and amplitude is large when denominator is small. Denominator is small. So if we see graph of this, you will get graph like this. Means here we have taken amplitude of oscillations and here frequency. You will observe amplitude goes on increasing. Amplitude goes on increasing and it reaches a maximum value and then it decreases. So here also we have amplitude. Here so I have three graphs. Now three graphs, here we know, here factor gamma is also there at the denominator. Gamma is what? R upon 2m. So that depends on damping. So inverse relation. So when damping is more, amplitude is less. When damping is less, amplitude is more. So what happens here? This is for low damping. This is for high damping. High damping. This is for high damping. This is for medium damping. And this is for low damping. So here frequency of applied force on this axis, amplitude on this axis. So see here, amplitude is maximum here for low damping, maximum here for low damping, maximum here for low damping. So what happens here? Amplitude is maximum at certain frequency. Certain frequency. And this is maybe equal to natural frequency. And this is called resonance. This is called resonance. So what is resonance? When frequency of applied force is equal to natural frequency of oscillations, oscillator oscillates with maximum amplitude. That is simply called resonance. Now what happens to phi with frequency? We know tan phi is equal, phi is equal to, I will take phi is equal to tan inverse 2q gamma upon omega 0 square minus q square. Now we know here q can be less than omega, q can be greater than omega. Now here, since it depends on this difference, as we go away from this q equal to omega 0, that difference goes on increasing between omega 0 and q, amplitude goes on decreasing. Similarly here, if we go on this side, difference between omega 0 and q goes on increasing. It may be negative. Here it is positive, means here omega 0 minus q, here omega 0 minus q. Here it is negative. Here it is positive, here it is negative. Here it is negative. Omega here it is negative here and positive here. Omega 0 minus q. But what happens here? We have square. So maybe negative, but its square it becomes positive. So that increases on both sides. So amplitude decreases. What happens to tan phi? Tan phi. So if we plot graph of phi versus q, and suppose we take here pi by 2, here pi, it is 0. And here suppose we take q is equal to omega 0. That is frequency of applied force is equal to natural frequency of oscillations. And at that point we get resonance, means maximum amplitude. If we see here, this one. Now this term, it is q is less than omega 0. So here this is positive. So what happens here? Q less than omega 0 means omega 0 minus q, or omega 0 square minus q square is positive. So this whole term is positive. And if we see your angle, it lies between 0 to pi by 2. So if we plot graph, you will get graph like this. Go on increasing frequency. Go on increasing frequency. Phi will go on increasing. It will become pi by 2 when q is equal to omega 0. We know q is equal to omega 0 means term upon 0, that is infinity, and tan inverse infinity, that is pi by 2. And as we go here, graph will be like this. It will go towards pi. So this is graph. Now this also depends on this factor gamma, damping. So when damping is more, you will get graph like this. For less damping, this is for less damping. When damping is high, you may get graph like this. So here this is for high damping. And finally it will go to pi by 2, pi, and here it is 0, but shape of curve will be like this. For this is high damping, this is for low damping. So this is nature of the graph between pi and q. So in this way we get amplitude versus frequency graph, phase versus frequency graph. Now we have two types of resonances, that is amplitude resonance and velocity resonance. Velocity resonance. Velocity resonance. Now we will go to amplitude resonance. What is resonance? When frequency of applied force is equal to natural frequency of oscillator, oscillator oscillates with maximum amplitude. That is called resonance. Now we will see amplitude resonance. Now here A is equal to F0 upon square root of omega 0 square minus q square bracket square plus 4q square gamma square. So this is the case. Now amplitude will be more when denominator is less. Amplitude will be more when denominator is less. So we can see condition for less denominator, because denominator it is what? This, if we take this term, it is function of q, and we change q and we see amplitude. So you can have condition for less denominator. D by dq of omega 0 square minus q square bracket square plus 4q square gamma square, and equate this equal to 0. For less denominator means more amplitude. For less denominator means more amplitude. And you will get here from this. So if you go through textbooks, you will get this whole derivation and so on. Here we will consider only final term. So you will get q is equal to square root of omega 0 square minus 2 gamma square, or it is also equal to omega 0 square minus r square upon 2m square. So here for small damping, this q, it is slightly less than omega 0, slightly less than omega 0. So I will call this is frequency at which amplitude is maximum. Let us call this as QR. QR. So if we plot graph of here, amplitude versus frequency. So here this point is Q is equal to omega 0. Here amplitude will be maximum for frequency which is slightly less than omega 0, and that is due to what? That is due to damping. That is due to damping. When damping is small, very small, r square upon 2m square is very small, and you can take qr equal to approximately equal to omega 0 for very small damping. Very small damping. qr is equal to approximately equal to omega 0 for very small damping. And here, so what happens here, QR will be equal to omega 0 for small damping, and resonance will take place, amplitude will be maximum, and somewhere here we will have maximum amplitude. Let us call that as A max. A max. So what is A max? A max will be equal to F0 upon, now here this first term will be 0, nearly 0. So square root of this. So we'll get what? 2 omega 0 gamma. Omega 0 gamma. Or you can take here F0 upon omega 0 R by M, because 2 gamma is M. So it is MF0 upon omega 0 R, and you can take A max is equal to F capital F0 upon omega 0 R, where capital F0 that is amplitude of applied force, and small f0 that is f0 upon m. Small f0 is equal to. We have seen this. So, and this is called amplitude resonance. So amplitude will be maximum here for frequency of applied force is equal to natural frequency, and that maximum amplitude it is either this or this or this when damping is small. But when damping is not small, you have to use this Q here, here, and we have to find that A max, Now next one, that is velocity resonance. And we know displacement of forced oscillator, it is x is equal to A sin qt minus phi. What is velocity? We know velocity it is dx by dt. So velocity we can write from this dx by dt. So aq cos qt minus phi. And now again this cos qt minus phi, it depends on what? Frequency of applied force, and we know it varies between +1 and -1 through 0. So what happens? V will varies between plus AQ. So V will vary between plus AQ to minus AQ through 0. It will vary like this. Plus AQ to minus AQ. So we will call this AQ as velocity amplitude. So I can write V is equal to V0 cos qt minus phi. Cos qt minus phi. So V0 is equal to what? AQ. Now if we take this AQ, you will get V0 and we know amplitude is what? This. So V0 is equal to AQ. So use this here. So V0 is equal to F0 Q upon square root of omega 0 square minus Q square bracket square plus 4Q square gamma square. Now let us take this Q at the denominator. So we will get here V0 is equal to F0 upon 1 by Q into square root of omega 0 square minus Q square bracket square plus 4Q square gamma square. So we will get V0 is equal to F0 upon. Now you can take this 1 by Q inside. It becomes 1 upon Q square. And if we adjust terms, you will get omega 0 square minus Q square bracket square and multiplied by 1 upon Q square. So I can write like this. Plus 4 gamma square. So again see, V0 depends on this term. V0 depends on this term. So if we plot graph of velocity versus frequency of applied force, and if we see this nature, when denominator is small, velocity amplitude is large. When denominator is large, velocity amplitude is small. So if we go on plotting the graph, you will get graph like this. And somewhere here, your velocity amplitude will be maximum. Let us call this as V0 max. So you can find similarly using this condition d by dq of omega 0 square minus q square bracket square upon q plus 4 gamma square, equate this is equal to 0. That is condition for minimum of the denominator. And you will observe, if we solve this, you will observe that at omega 0 is equal to q or q is equal to omega 0, when frequency of applied force is equal to natural frequency, you will get actually here. So here q is equal to omega 0, you will get maximum velocity. Now what is this Vmax? So you can find Vmax using q is equal to omega 0. So if we take this one, put q is equal to omega 0 here. So this first term in the square root is 0. So 2 gamma square. So we will get f0 upon 2 gamma. f0 upon 2 gamma. If we use gamma, 2 gamma is equal to r upon m. We will get this as f0 upon r. So this Vmax is equal to f0, capital F0 upon r. This is maximum velocity. And what is phi? Phi we know, it is tan inverse of this. So here at resonance, phi will be pi by 2. Phi will be pi by 2. So this is about velocity resonance. So velocity resonance takes place when frequency of applied force is equal to natural frequency. Your velocity amplitude will be maximum. Velocity amplitude will be maximum. And also we have seen amplitude resonance. For small damping, amplitude is maximum when frequency of applied force is equal to natural frequency of the oscillator. So this is about velocity resonance. Now we'll go to next term, that is power and bandwidth. We know in forced oscillations there is driving force which is continuously applied to oscillator to oscillate in external resistive medium, and we know f0 sin qt, it is applied force. f0 sin qt, it is applied force, and due to that force oscillator will oscillate and will get x is equal to a sin qt minus phi. And if we plot graph of x versus t, you will get sine curve. x versus t. This is one cycle of oscillation. So this part, it is one cycle of oscillation. And what happens here in forced oscillator? Oscillator oscillates with frequency equal to frequency of applied force. So due to external periodic force, energy is continuously supplied to the oscillator. Means power is supplied with time. So power is absorbed by the oscillator from external periodic force. In general, power is force into velocity. What is force applied? That is F0 sine qt into dx, and velocity is dx by dt, and we know this x. This is x. Now what happens? Here x is simple harmonic term. So dx by dt, it also varies with time. So we take average power absorbed over one cycle of oscillation. Over one cycle of oscillation. So we have to take its average. So we take average of this over the cycle of oscillation. Now f0 sine qt, you can find dx by dt. So we know dx by dt is equal to aq cos qt minus phi, and use this here. And then take average of sine. We know average of sine square qt over one period of oscillation, it comes out to be 1/2. So use that one here. You will get average power. P bar is equal to 2a square q square upon 2. P bar is equal to r a square q square upon 2, where r is damping, a is amplitude at that frequency, and q is frequency of applied force divided by 2. So this is power absorbed by the oscillator. Power absorbed by the oscillator. So we know A, we know already. So if we use that A here, we get P bar is equal to A square, because we know A is equal to F0 upon M under root omega 0 square minus Q square bracket square plus Q square R square. R square by M square. Omega 0 square, like this, Q square R square. So if we use that here, and if we adjust terms, you will get P bar is equal to this. You will get P bar is equal to this. That is R F0 square, here capital F0 square upon 2m square in bracket omega 0 square minus Q square bracket square divided by Q bracket square plus R square upon M square. So here this is power absorbed by the oscillator. Now if we see, power also depends on this difference. And when denominator is small means difference between omega 0 and Q is small. Power is more power is absorbed. So if we see graph between P and Q, P bar and Q, P bar and Q, you will get graph like this. And this power will be maximum when denominator is small. When denominator is small, the smallest. So from this you can use a condition for minimum denominator. You will observe that at Q is equal to omega 0, power will be maximum. Here Q greater than omega 0, here Q less than omega 0. And see here we have omega 0 square minus Q square bracket square. Here omega 0 minus Q, it is positive, here it is negative. But since there is square, it is positive, and when omega 0 minus Q, it goes on increasing, power goes on decreasing, power absorbed by the oscillator. So at Q is equal to omega 0, power is maximum. And we know velocity resonance as well as amplitude resonance takes place at natural frequency. Means when frequency of applied force is equal to natural frequency of oscillator. So when frequency of applied force is equal to natural frequency of oscillator, oscillator absorbs maximum power. And what is that P max? What is that P max? So use simply Q is equal to omega 0 here. You will get P max. And that P max will be equal to, if we find this, P max will be equal to so simply use this term will be 0. So RF 0 upon 2m square, R square upon m square, 1 R will cancel, m square will cancel here. So we will get F0 square upon 2R. F0 square upon 2R. That is this one. Or you can write this as this is also equal to, if we write in terms of factor gamma, you can find that because gamma is equal to R upon 2m. So R is equal to what? 2m gamma. So you can write here P max, means simply put omega 0 here. So we will get here P max is equal to m F0 square upon 2 gamma. This is P max in terms of gamma. That is maximum power. Now we'll see what is bandwidth. What is bandwidth? So this is power. It is in terms of gamma, or you can take in terms of R. And we have seen this is graph of P bar versus Q. And here at Q is equal to omega 0, power is maximum. P max. P max. Now, what is bandwidth? What is bandwidth? So, if we go away from natural frequency, means frequency of applied force, if we go on increasing or decreasing, means here frequency difference omega 0 minus q, if it goes on increasing on both sides, power goes on decreasing. And here there are some frequencies. One is greater than omega 0, another is less than omega 0, for which power falls half of its maximum value. So here P max divided by 2. P max divided by 2. So here you will have two frequencies. One frequency, let us call this as Q1, and this frequency, this as Q2. So Q1 and Q2, these are two frequencies of applied force at which power is half of maximum value. Now Q1 is less than omega 0, Q2 is greater than omega 0. So we define bandwidth delta Q. It is Q2 minus Q1. What is meaning of this? What is meaning of this? Bandwidth, it is the difference in frequencies for which power falls from maximum to half of maximum. So this difference, if we take, this difference is delta Q, and this is called bandwidth. This is called bandwidth. And here this bandwidth is very important in forced oscillations. Now for some forced oscillations, you may get graph like this. Generally in radio oscillators, means radio receiver circuits, you will get graph like this. Means what happens here? Bandwidth is very small. Such a resonance is called sharp resonance. You may have graph like this. That is called flat resonance. So that are very important. Bandwidth is very important in forced oscillation. That we will see in next lecture. So this is about bandwidth. Now you can find value of bandwidth delta Q. So here at this P max upon 2. So let us take Q is equal to Q1, use here and take power half of maximum value. You will get delta Q, that is bandwidth. Bandwidth is equal to 2 gamma. Or delta Q is equal to R upon M. So bandwidth, it is inversely proportional to mass, directly proportional to damping. When damping is more, bandwidth is more. When damping is less, bandwidth is less. Now we have another term that is called quality factor. We define quality factor. Q is equal to 2 pi E bar, that is energy stored in the oscillator, divided by dissipation of energy in one cycle of oscillation. Here we have minus sign. Minus sign means minus dE bar by dt, that is rate of decrease of energy, multiplied by period of oscillation. This gives you dissipation of energy. In one oscillation. And here it is average energy stored in the oscillator at that time. So we know x is equal to a sin qt minus phi dx by dt is equal to aq cos qt minus phi. Then you can have potential energy capital V is equal to 1/2 kx square, kinetic energy it is equal to 1/2 m omega square v square, that is dx by dt square. And then use this one here, x and dx by dt, and find total energy. Total energy what? Ke plus phi. And then take average of that. And d bar by dt is what? We know damping force is what? R into dx by dt. This is damping force. So simply damping force into velocity, that is power dissipation, that is also rate of change of energy. So if we find all these and if we use in above equation, you will get quality factor is equal to mq upon 2r in bracket omega 0 square upon q square plus 1. So you can write q is equal to small q upon 4 gamma in bracket omega 0 square upon q square plus 1. And at resonance means q is equal to omega 0. You will get quality factor, use here q is equal to omega 0. So 1 plus 1, that is 2. 2 will get cancelled. So you will get m omega 0 upon r. Or you can take here omega 0 upon 2 gamma. This is quality factor. Okay, so here this is some theory about forced oscillations. In next lecture we will see some sharpness of oscillations, sharpness of resonance curve, and then we will go for multiple choice questions. So to solve multiple choice questions, you must know all theory behind it. Then you will be able to solve multiple choice questions. Now is it clear to you? Vijay?
Yes sir.
Okay. Actually, ही जी थेरी तुमची सगळी SY ला झालेली होती. ओके, SY ला ही सगळी थेरी झालेली. आता याच्यावर आपण फार केअरफुली एकदम जे जॅमला विचारलेले काही ऑब्जेक्टिव्ह प्रश्न आहेत ते घेऊन प्लस ऍडिशनल मी काही प्रश्न टाकेल, हे पुढच्या लेक्चरला आपण घेऊ. ओके, पुढचं लेक्चर तुमचं मंगळवारी घेऊ. ओके, आणि थोडं जास्त वेळ घेऊ मंगळवारी. ओके, चालेल.
ओके सर.
इथे थांबू आपण.
ओके सर.
ओके, थँक्स. विल स्टॉप हिअर. कोणाला काही प्रश्न आहे का?
थँक्यू सर.
ओके, प्रश्न नाही ना कोणाला काही?
थँक्यू सर.